Okay, so we'll talk about hypothesis learning. So what do we mean by hypothesis learning? So it's like some type of logical inference which is used in learning. Okay, so you may have a hypothesis. So when you talk about a hypothesis, it's something like saying if we have say we may have a hypothesis like this. Okay, so in other words, you're saying that all the patterns here belong to, say, class plus, and the ones outside this belong to class minus. So what you're going to basically do is that you're going to represent this hypothesis by using some logical sentences. For example, depending on the features, you may say if the feature 1 is so and so, is less than so and so, or greater than so and so, etc. And you are going to represent the hypothesis by a set of such sentences in logic. Okay, so you are going to use a set of logical sentences. So everything is by use of logical sentences. So what we are going to basically talk about is how do we find the hypothesis for a particular class. Okay, in suppose we have a set of training examples. How do we find the hypothesis to represent those training examples? So this is done by an incremental construction, okay, of the hypothesis. So we'll see different ways basically of doing this. So the hypothesis is of this form basically, okay, that is for all x, goal x, if and only if Cf of x, right. So each hypothesis says that a certain set of examples will be the goal predicate basically, okay. So the hypothesis space will consist of a set of hypotheses like this. It's H1 or H2 or H3, etc. Okay, so altogether they form what is called the hypothesis space. So now suppose we have an existing hypothesis H, right? Now when you get a new example, the new example can either be classified correctly by the hypothesis which is there, or they may be, if it is inconsistent, there are two cases. It can either be a false negative or a false positive. Okay. So when you say that an example is a false negative for a hypothesis, it means that the hypothesis says it's negative, but it's actually positive. And when you say it's a false positive, it means the hypothesis says it's positive, but it is actually negative. Okay. So then we need to change the hypothesis so that it is consistent with these examples also. So how do we go about doing this basically? Okay. So here suppose this is the hypothesis that we have, right? Now you have got a new example, okay, which is put over here, right? So this one is this one is actually a false negative. It should have been positive, but it has been classified as negative. So when you get a false negative, what you need to do is you need to include this into your hypothesis. Okay, so which means you have to do what is called generalization. Okay, that's and suppose you have a false negative, okay, or a false positive. It should have been negative, but it is put as positive. Then you need to remove this value. Okay, so this is what is known as the specialization. Okay, the hypothesis is specialized, so it's made much smaller. You can see here it's made bigger. In this case, hypothesis is made little smaller. So you have to carry out either specialization or generalization of the hypothesis. So we can say the algorithm is something like this. So if A is consistent, you don't do anything, but if it is false positive, then you do specialization. If it's false negative, you do generalization basically, and you return H dash, okay, after doing that. So this is the learning algorithm, and this is known as the current best hypothesis learning algorithm basically, okay. Then the next thing we are going to see is what is called the version space learning. So in the version space learning, what you are going to do is you are going to keep a hypothesis which are consistent with the data so far you have to see. Okay, so what you do is you are keeping like all the examples in your data set, you are going to keep it as hypothesis, right? So you can say that you have your hypothesis as a disjunctive sentence H1 or H2 or H3, etc. Okay, and then you check each new example, okay, with this set of hypotheses that you have, okay, and if you find that any of the hypotheses are inconsistent with this new example with which you are checking, you remove that hypothesis, okay. So you are then going to shrink the hypothesis till you come up with the hypothesis which is consistent with all the examples that you have, okay. So this type of learning is called the version space learning, okay. It's also called the candidate elimination algorithm, basically version space learning algorithm or the candidate elimination algorithm, okay. So this we can see that it's an incremental process basically. Of course, you may have problem with a very large hypothesis space. If you are keeping everything, okay, if you are keeping everything that is there as H1 or H2 or H3 up to Hn, you may find that n is a very large number, okay. So this may be a problem in some cases, okay. So this gives you a version space. So you are including H in the version space if it is consistent with E, right, with every E that you are going to send to this. Next is what is called the least commitment search, okay. We know that if we look at the hypothesis space, okay, there is an ordering in that, namely generalization and specialization, okay. So when you look at the boundary, okay, of your set of hypotheses, it may not be a point, but it could be a set of hypotheses which is called the boundary set basically. So you can represent the version space that we are talking about by two boundary sets, okay, a most general boundary and a more specific boundary, which is called the G set and the S set. And everything that comes between this G set and S set will be consistent with the examples that we have seen, okay. Okay. Each member of the S set is consistent with all observations so far, okay, and there are no consistent hypotheses that are more specific than that, okay. Every member of the G set is consistent with all observations so far, and there are no consistent hypotheses that are more general than that, okay. So how do we start doing this? We need to actually set up the G set and the S set to start it, okay, and then see every example, okay. So what you do is you set up the G set to contain true, which means it contains everything, and the S set to contain false, which means it doesn't contain anything as of now, okay. So this is how your G set and the S set is. So, your hypothesis and all the examples that you have will fall between the G set and the S set, and everything which falls out of this region are all this is the inconsistent region that we are talking about basically. So, what do we do? So, every consistent hypothesis is more specific than some member of the G set and more general than some member of the S set. Okay. So, every hypothesis is more specific than some member of the G set and more general than some member of the S set is a consistent hypothesis. Okay. So, what we do is that you need to be able to update your S and G whenever you get a new example. Okay. So, if you find that the new example is consistent with the G set and S set that you have, then you don't need to do anything. Okay. It's only if it is not consistent. So, when you get a new example, then what is it that you basically do? Okay. So, we need to worry about the members Si and Gi, that is all the members of S and all the members of G. Okay. For each one, the new example, you take the new example, okay, and you take each of the Si and you check if it is a false positive for Si. Okay. So, if it is a false positive for Si, it means Si is too general, right? But there are no consistent specializations of Si. So, we throw it out of the S set. Okay. So, Si is removed from the S set. If it is a false negative for Si, this means Si is too specific, so we replace it by all its immediate generalizations, provided they are more specific than some member of G. Okay. Then you check if it is false positive for Gi. This means Gi is too general, so we replace it by its immediate specialization. False negative for Gi means Gi is too specific, but there are no consistent generalizations, so we throw it out of the G set. Okay. So, what we do is every new example that you get, you check whether it's a false positive, false negative for every Si, and if it's a false positive or false negative for every Gi, and take the action to update your S and G sets according to that. Okay. So, if you keep doing this for every new example, then finally you will be left with one hypothesis which will be your unique hypothesis which your data set will follow. Otherwise, the version space will collapse, which means either S or G becomes empty, which means there are no consistent hypotheses for the training set that you have. Okay. So, it means that it has failed in finding a consistent hypothesis, or you may run out of examples and you may have several hypotheses remaining. Okay. So, you are saying that the version space represents a disjunction of hypothesis, and for any new example, if all the disjuncts agree, okay, then we can return that disjunct as your hypothesis. So, what are the disadvantages of using this LCS? Like we said that first of all, it may collapse, right? The version space will always collapse if you don't have enough examples, right? Or enough attributes if you don't have. Okay. And then the number of elements in the G set or the S set may grow exponentially in the number of attributes. Okay. So, then these are some drawbacks which we need to keep in mind for these problems basically. Okay. So, this is about the version space. Now, I'd like to talk about the class imbalance problem when it comes to learning problems, right? So what is this class imbalance problem? So suppose you have a training data, okay, so usually we may have say something, if we have two classes, say class 1 and class 2, okay, we may, if you have equal number of examples, okay, of class 1, if you have equal number of examples of the two classes, then you say that it's balanced, right? Your data set is balanced. So you have equal number of examples of both the classes. But suppose one class has a lot of examples and another class has very small number of examples, then we say that it's a class imbalance problem. Okay, that means one class has got very few number of examples in it. Okay, it's also possible with more than two classes. Okay, so you can have 3 or 4 classes, and you may have one class which has less number of examples, right? Or you can have one class which has larger number of examples. Okay, so first of all, if we take the example of having two classes, right, we can say that if you consider them to have two classes, positive and negative, right, then we can say that if positive number of positive examples, number of negative examples are equal, you call it a balanced data set. But if one label is more common than the other label, it's imbalanced. And generally what you call is, you call them the majority class and the minority class. So the class having more number of examples is called the majority class, and the one which has the less number of examples is called the minority class. So when you have a class imbalance problem, what happens to the classification which you are going to carry out? Okay. So you find situation where one class is more represented than the other class. Okay. So you find that the classifier is more biased towards the majority class. Okay. So what happens is that you may find that the majority class is being classified properly because it's a predominant class, and your classifier may be more biased towards that because it has more number of examples of that class, and it may be performing poorly on the minority class. Okay. And you may find patterns on the majority class are classified correctly, but examples from the minority class may be misclassified. And this type of thing is not good when the minority class is very important, right? For example, if you take things like fraud detection, right? So you have credit card fraud detection. So you have so many people's credit card information, but the fraud may be just one here or there, right? Maybe 99% of the data is without fraud, and it may be just 1% where you have fraud, right? So if your data set is like that, you may find that the 99% of your data is being classified correctly, the majority class, but the minority class may not be classified correctly. Similarly, anomaly detection, that is something like fraud detection, right? So the anomaly, you find that anomaly exists in just a few examples. Most of the examples will be normal, right? The quality check that is done in the factories, etc., you find most of them are normal. There will be one input here or there which is abnormal. Medical diagnosis also, for example, you may find that if you have say ECG of a number of n ECGs, right, of n people, you may find that the detection of heart problem may be there in just a few, most of them may be normal, right? But whenever a person has a heart issue, it's very important that it should be classified correctly. Okay. Also, if we take the classification accuracy, okay, so suppose we have 99%, okay, is say without fraud, okay, so normal transaction, normal credit card, right, and 1% is with fraud, right. Now, if this 1% is classified incorrectly, you still get 99% accuracy, right. So, obviously, this 99% accuracy which we are getting here is not what we should be looking for. Basically, we should see how this 1% is being classified, right. So, using the usual classification accuracy, so this is your classification accuracy, right. So, using this classification accuracy may not be a good thing in this case, right. So, you have to see what evaluation metrics are better to be used when you have imbalanced data sets, okay. So, what are the various approaches that you can use to take care of this class imbalance problem? Of course, like we said, the evaluation metric is one which we need to see, but can we somehow balance the data set? So, that is what is done, or is there any classification algorithm which can be used on imbalanced data set without affecting the minority class, okay. So, generally there are, first type of approach is what is called the resampling approach, okay. So, in the resampling approach, you are going to add patterns or remove patterns so that you can balance the data set. First one is what is called the oversampling, okay. So, what you do is you take the minority class and you add more examples, right, whichever way you do it. And undersampling, where you take the majority class and you remove some of those patterns, right. So, that becomes undersampling. Otherwise, you can create synthetic data generation. You create synthetically new examples of the minority class, okay. So, and active sampling is just to keep seeing which is how much majority, how much minority class samples are there online or while you are doing the algorithm, and then try to balance that, okay. So, that is at the data level. At the algorithm level, you can use what is called cost sensitive learning, okay. So, you are assigning different weights to different classes, okay, during training to penalize the misclassification of the minority class more heavily, okay. Next is to use ensemble methods, okay. So, you have multiple modules, and in each module you take a different subset of the data, so that you have them balanced basically, okay. And then you combine all the classifications that you get. Third one is to use what is called a loss function that gives more weight to hard examples, okay, that is those misclassified with high confidence, and less weight to easy examples. So, this is like saying each example is given a weight, okay. So, that is something like what we do in things like adder boost, etc., where each example has a weight given to it. And you can use other approaches like batch size considerations, ensuring that each batch contains sufficient examples of the minority class. So, that is something like ensemble learning. And you carry out feature selection, identifying and using only the most relevant features, okay. So, these are all the several approaches that can be used for this type of a problem. So, let us see what we do for oversampling basically. So, oversampling involves increasing the number of instances in the minority class. So, what are the different techniques that you can use? Simple duplication is one, Okay. So at random you take some of the existing examples in the minority class and put put the same example again, keep repeating the existing examples so that you have equal number of patterns finally of the majority and the minority class. Second one is what is called SMOTE. SMOTE is synthetic minority oversampling technique. So you are creating new synthetic samples, okay, of the minority class so that you can balance the two. One of the advantages of oversampling is that it can improve the model performance on the minority class, okay, but it can also lead to some type of overfitting, okay, because when you add synthetic examples or when you keep duplicating the same examples again, it may not represent the true distribution of the minority class really, okay. So let us see how the SMOTE actually works, okay. Synthetic minority oversampling technique. So first you select one random instance within the minority class, okay, and identify k neighbors of this. Then you select one of these neighbors at random, right, and you take the distance vector between this data point and that neighbor, okay, and you get one value which is on that line, okay. So we can say it's something like this. So we have xi is the point which is selected and you have chosen some neighbors of that. So these are all the neighbors of that pattern. So if you have chosen xzi, you have this line joining these two. So you find the new point which is on this line, right. So you find something like, find some cutoff point, okay, or some point here, some ratio you use and find some point on this line and take that as a new example that you are using, okay. One more method that you could use is that you take, like they say, choose some point and find the k neighbors of that and find the average of those k neighbors, okay, and that point can be taken as your new point, okay. So in this way some different methods can be used for finding the new point basically. The next method is undersampling, which involves decreasing the number of instances of majority class. The first one is called the random undersampling. So randomly you remove some instances from the majority class so that it has less number of patterns or equal to maybe the minority class. Second one is what is called the Tomek links. So what you do is you identify instances which are very close to each other in the majority class, okay. So this makes sense because similar points are being removed, and one advantage could be to reduce the training time and complexity, okay. But you may lose some potentially useful information, okay, because you are removing some patterns from the majority class which may be having some useful information, and it may cause some difference in the distribution of the majority class basically. So these things will have to be taken into account, okay. So what are the considerations we need to keep in mind when you look at the class imbalance problem? How much imbalance is there, right? The severity of the class imbalance affects the choice of resampling techniques, okay. If the severity is too much, then you may have to sometimes use a hybrid approach. Maybe you have to use both oversampling and undersampling, or and also maybe you need to use some algorithm which can be used when there is imbalance, etc. The next consideration is the data set size. Oversampling is generally most suited for smaller data sets, because if you do oversampling, you may find otherwise that the data set becomes too large, whereas undersampling is more suitable for larger data sets. If the data set is really extremely large, then you might as well reduce the size of the data set by doing undersampling. The third one is model performance. The effectiveness of resampling techniques depends on the specific model which you are using. Okay, so what is the model you are using for classification over there? So you need to see that. And then you also have the risk of overfitting. Okay, it can lead to overfitting if not used carefully, because when you're increasing, when you're doing over sampling, you may be actually producing so many samples of point which is not important, okay, and it may change the distribution of your minority class specifically. And if you do undersampling also, it can lead to overfitting, because you may be removing some useful information that you have. So these are the considerations which need to be taken into account. Whenever you get a data set which you use for imbalanced data sets, so generally when you have researchers working on imbalanced data sets, what they do is they use some benchmark data sets which are available online, and you can use different techniques of balancing the data set, and you could compare it and see which method is doing better, etc. Or if you have some algorithm of your own, you can check it out by comparing it with existing algorithms. So the first thing these people give in the benchmark data sets is what is the imbalance ratio, right? So most of the work on imbalance data sets is restricted to two classes, though there are ones which are worked with more than two classes basically. Now let us look at some of the evaluation techniques which you can use when you are using an imbalanced data set. Okay, so like we said, using the classification accuracy does not make sense in an imbalanced data set. So what are the things that we can use? Okay, so here this is what is called the confusion matrix. Okay, so this confusion matrix actually divides the data which has been classified into TP, FP, Fn and Tn. Okay, so that is the true positive, the false positive, the false negative and the true negative. Okay. Now if we add all these four up, we get the total number of examples that we have in the training data, right. So if we look at true positive, it means these are the cases in which you have predicted positive. Okay. So in other words, it was actually positive and you have predicted it as positive. So that is called the true positive. But now suppose it was actually negative but you have predicted it as positive. It's called a false positive. Or you could have it could be actually negative and predicted as negative, right? So that should be the true negative. Or it could be actually positive when it has been predicted as negative, which is equal to Fn. Okay. So if we look at the classification accuracy of this data set, right, it would be actually equal to Tp plus Tn, which gives the number of examples which have been classified correctly, divided by Tp plus Fp plus Fn plus Tn. So this gives your classification accuracy that we have, right. Now there are some other evaluations metrics that we need to see. one is what is called the precision. Okay. So this has the ability to retrieve patterns that are most relevant, right? So precision is equal to true positive divided by true positive plus false positive, right? So it means precision is the ratio of what has been uh, classified correctly divided by what actually should have been classified positive, right? So that is the precision. Then we have the recall, the ability to find all of the relevant items. Okay, in other words, it's TP divided by TP plus F1. Okay, so this one basically. Okay, so this gives you a recall. So in the case of imbalanced data sets, you can check out the precision and the recall. Okay. So what you want is you want the precision recall both to be as high as possible basically. Okay. Another thing you have is what is called the F measure. So the F measure is actually the harmonic mean between the precision and the recall. Okay, so that is 1 over half into 1 by r plus 1 by p. So it will be 2rp divided by r plus p. So this one you want it to be as high as possible, the F measure basically. So this is another important evaluation metric. So why do you use the harmonic mean? The harmonic mean emphasizes the importance of small values, okay, whereas the arithmetic mean is affected more by outliers, which are usually large. Okay, so in the case of harmonic mean, both need to be high for harmonic mean to be high, okay. So that's why R and P both have to be high. So here is an example where you have true positive is 1 and true negative is 90 and false positive is 1 and false negative is 8, right. So the accuracy will be 90 plus 1, 91 divided by 99, okay, 100 basically, okay, which is 0.91. Precision is actually half and recall is 1 by 9, okay. And this is what is called the ROC curve. So that is the false positive rate by the true positive rate, okay. So what you want is, the ideal situation is to have a curve like this basically, okay. It means that it's perfectly able to distinguish between the positive and the negative class, okay. And this is the worst that you can basically have, okay, where area under the curve is approximately 0.5, okay, that's half the amount, and model has no discrimination capacity to distinguish between positive and negative class. So then usually you get curves like this, ROC curves, and the higher this curve is, okay, the higher this curve is, for example, if you have a curve which comes below this curve, right, you may have a curve which comes below this curve, then you say the one which comes above or closer to this one here is the better ROC curve, okay. For example, you have here different ROC curves, okay. So you can see that this one which comes closer to this one here is a great model, and this red one is a good model and this green one is a bad model basically, okay. So what we want is some thing where the ROC comes closer to the 1.0 here basically, Okay, next is the cost sensitive learning. Okay. So we need to minimize the expected cost of misclassification. So what you do is different kinds of classification errors have different costs. Okay. So you use this cost sensitive method to evaluate it. Okay. For example, you could use it in medical diagnosis basically. Cost of false positive error. Okay, when you say it's a false positive, in other words, you are saying the person has the disease when the person really doesn't have. Okay, so it leads to unnecessary treatment, unnecessary worry. But if you have false negative, it means that it has not been diagnosed, right? So when it is not diagnosed, it may lead to death, it may lead to lot of complications, right? So this is actually a very important point to be taken into account. In fraud detection, false positive means resources are wasted investigating something which is not really a fraud. And if it's a false negative, it's a failure to detect fraud, which may be a very expensive because the person may be carrying out fraud and getting away with it, right? So you find that both these need to be detected, but detection of false negative is actually very important, right? So here you have the cost matrix, okay, where you have um, what you are doing here is the true positive is being given a cost of -1 and the true negative is being a cost of 0, whereas if it is negative and it is given as predicted as positive, you've got a high cost, right? And you have a cost in this way, right? So when you are using this type of a thing, you may find that if you take this confusion matrix and this confusion matrix, so what you find here is basically most of the patterns are falling along the true positive, true negative, right? Um, so whereas in this case you find that there are more patterns, I mean it seems to be more imbalance. So you find that if you use the cost for evaluation, you find there's a variation in this. If you go with the accuracy, you will go with the model 2 basically, okay. However, if we are focusing on the cost, then we will go with the model 1 because model 1 has less cost than the model 2 basically, okay. So this is the cost matrix that we are using, okay. So these are all the methods that we use to deal with the class imbalance problem. So we'll stop here at this point.